Bismillah ar-Rahman ar-Rahim. Assalamu alaikum. And today we're going to talk about chapter 6, which talks about trigonometric ratios or trigonometry in general. And I wrote this as an introductory, as an introduction to before we actually dive into the main topics of today. And that trigonometry in general deals with ratios in general. Because if you were to look at the essence of what sine, cosine, and tan represent, they're just ratios between different lengths of height, or like just different lengths in general. So if you look at sine, it's the ratio between the opposite side with respect to the angle you're looking at over the hypotenuse. And with cosine, it's the adjacent to the hypotenuse. And with the tan, it's to the opposite and adjacent with respect to the angle you're looking at. So in general, you're dealing with ratios. But what if we're dealing with triangles in general that aren't right angled, as in we don't have this? So we're going to look at such rules, which are actually derived either ways from Pythagorean theorem, and we're going to see how we could just basically toy around with the triangles we have such that we come up with formulas. So let's say I want to find the length of any given side of a triangle when I'm given either two given sides and one unknown angle, or the other way around. It doesn't matter. And this rule is called the cosine rule because it consists of the cosine of an angle with other with other stuff. So let's say I have this triangle. I have sides of lowercase a, b, and c, and the angles for each of these sides are labeled as capital A, because opposite, B, capital B, and capital C. And let's say I want to find the length of A or any other side, but let's just start with A because, just for simplicity. So, as I know, I can't really do anything with this triangle because it's a right angle. I cannot, I don't think so. I can do anything. So, what I'm going to do is I'm going to draw a line like this. I know it's not going to be straight, but let's say it's like this. And let's say I cut out a piece of the length side length C, and this is x. And now I have these two lengths split into x, and obviously if I subtract these two together, this will be C minus x. And this line is like drawn in such a way where you actually create two right angle triangles. Okay, and obviously there'll be an angle here and an angle here. So, and let's name this length right now h, as in like the height. And obviously h will be equal in both triangles, so let's create some formulas for them. So I have h here. Oh, give me a minute. So I have h squared, and let me just write down with a different color. I have h squared plus c minus x all squared equal to a squared. And also I have h in the other triangle equaling x squared, h squared plus x squared equals b squared. So I'm going to write that down as well. So I have h squared plus x squared equals b squared. And now since I have common terms of h and h in both triangles, I can just equate them to another and create a new formula. So if we just put these together, or let's just write here h squared equals a squared minus c minus x all squared. Now I can start equating them. So in the end, let me just do something like this. I'll have h squared equals b squared minus x squared and this is also equal to a squared minus c minus x all squared. And let's expand this. Let's expand this. I'll be left with b minus x all squared equals a squared minus, and we'll just open the bracket here. We'll have c squared minus 2cx plus x squared. And let's just close the bracket. So we'll have, and I forgot the squared here. So we'll have b squared minus x squared is equal to a squared. And let's just flip the signs for each term. We'll have minus c squared plus 2cx minus x squared. And you'll realize that we could cancel out x squared and x squared because they're the same in both sides. And in the end, what we're actually trying to find is the length of the side of a squared. Sorry, I was just stretching. So if we were to do that, whoa, what just happened? Now let's just send everything to the other side. So we'll have, or wait, there's no place here. Let's just continue down. We'll have a squared is equal to b squared plus c squared minus 2cx. Okay, and this is what we're left with. But where will the cosine come from? In here, we have x. If we look at the side or the length x, I don't know if you guys know this, but like basically any x component, since it's actually horizontal, like this, and also if we're going to talk about like any x or y component, and let's just say that there's a triangle here or whatnot. Whoa, what just happened? Wait, give me a minute. Any x component will be equal to what, like a, well, whatever it may be, cosine theta, and y is equal to like a sine theta, and a is just like the coefficient. Okay, so if we were to refer back to our triangle, or our this right angle triangle specifically, we know that we'll realize that x is equal to b cosine a, b the hypotenuse, and cosine a. So let's just replace x, because either ways x is really not a term that we actually know. It's just any arbitrary length that we took off from the original side or the original length of c. So if we were to replace it now, we'll have a squared is equal to b squared plus c squared minus 2bc cosine a. And what was the point of me proving all of this? Because to be honest, for me, when I took AS Maths back in the day, and that was just a few years ago, don't worry, I did not really understand the proof of this formula, so I just memorized it. And when I memorized it, without obviously understanding where it came from, I found it very difficult to like recall. I always had to actively recall the formula, and then obviously it's just like a hassle. Because what if you forgot what the formula is, or the order, or like the signs, but you can't prove it? Just as a last resort, if you want to make sure of the formula, you could prove it and then just reuse it. But obviously, I did not know how to do it back then. So the reason of me proving it is so you guys could understand where the rule comes from, and from there you could easily memorize it. So this is the cosine rule. That in the end, a squared equals b squared plus c squared minus 2bc cosine a. And a, b, and c could just be your random numbers or whatnot, but it all depends on what you take it with respect to. I mean, I could also readjust the formula such that it could be c squared equals b squared plus a squared minus 2ba and then cosine c. You know what I mean? So it depends on how you look at it. Which side are you calculating for? So as I said, a squared. Look, if you're going to deal with one side, then the squaring of both lengths will be added together, minus 2 of the product of both of them multiplied, and then cosine the angle opposite to what you're looking at. So if you're going to calculate for A, then you're going to look at this, and this, and this. You know what I mean? So yeah, that's the cosine rule for you. Okay, next rule we have is called the sine rule. And the same thing, from the highest point we have, we're just going to draw a line downwards such that we create a perpendicular angle. And before I go on, the reason why there exists two rules like cosine and sine is it just depends on what are the missing variables that you have to calculate for. If like there is like three sides, then obviously you don't need to use the sine rule, I'm assuming, since you have all three sides, you can easily calculate all three angles with the cosine rule with ease. But like if you have two sides and one missing angle, then I think so you could use the sine rule. Yeah, there's either always a section in the book where it says like under which scenarios are you going to use which rule. So yeah, anyways, since this is called the sine rule, let's just get the trigonometric ratios of the sine for each triangle, since obviously this is right angled. So let's calculate for sine with respect to this angle and this angle. So sine A is equal to h over b. And sine B will be equal to h over A. Since we have a common variable, which is h, let's just equate h to one another. So in this case, h will be equal to, or I don't even need to write the arrow thing, b sine A. b sine A. And here, h will be equal to a sine B. So we can equate h to one another. So we'll have b sine A is equal to a sine B. And keep in mind, this rule and how you'll actually get to form it depends on what is missing for you. Since I forgot to mention, our original assumption is to find the length of a side. So we're already assuming that we have the angles. We know what the angles will be like. So what I'll do here is that I'll just divide both sides by sine A and sine B. So if we get to calculate that after dividing them, we will be left with B over sine B is equal to A, let me write it properly, over sine A. And this is under assumption that we just want to find the sides. Because there are two forms of the final product of the sine rule. Once you get to simplify it even further, it depends on whether you're looking to calculate for a side or for an angle. Because if you're gonna calculate for an angle, then you're just gonna divide the sides in both sides, you know. So yeah, since we found A and B, and there's already a common theme that it will be B over sine B and A over sine A, we could assume, and this assumption is not based on nothing. We could actually even calculate the way you want to calculate for angle C is that if you cut B, if you draw a line from B, such that you also create a right angle triangle in both sides, and you're going to find out in the end that if you're going to get sine C, it will be H, and let me just flip the tab. It will be H over A, and in sine A, it will be, excuse me, H over B. So in the end, it won't make a difference. Or excuse me, triangle sine A, if you were to draw a line from B such that you create two perpendicular angles to create a right angle triangle, it will be sine A will be equal H over C. So yeah, if you were to simplify it and get the H term, since it's a common variable, you find that it will, in the end, you'll get the simplified rule to be C over sine C is equal to A over sine A. And since they're all equal to one another, so we can just assume that C over sine C. And this is for calculating side. For missing side. If you want to find the missing angle, as I said, you're just gonna divide both of these by their sides, and in the end, you're just gonna get the reciprocal of the original rule we have here, which is A over sine A. Oh, sorry. Sine A over A is equal to sine B over B is equal to sine C over C. And this is for missing angle. There you go. This is the sine rule that we have. And lastly, this is the last formula that we need to know in this chapter, is that the area of a triangle is equal to half the length of these two sides multiplied the sine of the angle between them. You see what I mean? Half times A times B, any two sides facing each other, multiplied by the sine of the angle between them. So it's half AB times sine C. And I don't really need to, is it worth proving? It's easy to memorize. So yeah, because either way, it will do the same step again. We're gonna do this, and just gonna calculate the area of both of them and simplify it and try to get a common variable and whatnot. So it's not worth the hassle. It's very easy to memorize. It's like it's very similar to the area of a right angle triangle, which is half times base times height, except, okay, apologies for the random pause, but there was just a power outage. But yeah, that's Egypt for you. Anyways, as I was saying, the formula of the area of any random triangle which is not right angled is either way similar to the right angle, which is half times base times height. So it's like the only component you're adding is just the sine of the angle between the two sides that you're already calculating for. So yeah, that's basically it. Let's just solve some questions and see how we could implement these formulas to find missing sides and angles. We have this triangle and we're asked to calculate the missing side, which is obviously this. So let's just name this X for now, and let's observe the triangle that we have here and see what we have. We have 108 degrees, which is the angle facing the missing side that we have. We have 6.5 and 5.6. Okay, so if you were to observe both rules that we found, or which is the cosine, we'll realize that since we're only missing one side, we have two given sides and an angle given. That means we are going to use the cosine rule, because otherwise, if we looked at the sine rule, what is it? For a missing side, we only have one given angle, and this won't really help us solve anything, because since we have two sides either ways, but it's like you're dealing with two missing variables and you have nothing else to equate it to. So that's why we're going to use the sine rule. So let's use the sine rule. We have x squared is equal to 6.5 squared plus 5.6 squared minus 2, the product of both sides multiplied one another, and sine the angle facing the missing side, which I think is sine 108, yeah. Oh, cosine 108. And you could obviously just put all of this under the square root, so there's no use for this. And let's input this in the calculator. And if you were just to round it, you'll get 9.8 and meters, of course. Let's not forget the dimensions, or the units basically. So yeah, this is how you solve using the cosine rule to find the missing side. Okay, in this question, it's actually a word problem, but I just put down everything that we need to know. So we have sides of AD of 75, DC 135, CB 60, and BA or AB 120. And we're asked to find the angle between BC and CD, which is basically this. And we were supposed to, yeah, as I said, we're asked to find this angle. How can we do so? We could create two triangles either ways. Let me just get a different color. If we connect the diagonal BD, we basically formed two triangles, and we're just going to use the cosine rule in both cases. Because either way, let's just name this to be x. You could use x, or we could use this triangle to calculate x, and then use the cosine rule in this triangle to calculate the missing angle. So let's do so. So we have x squared is equal to 75 squared plus 120 squared minus 2, the product of their multiplication, cosine 74. And obviously, if I were to send the squaring to the other side as a square root, we'll have x equal to, and let me just calculate it. The diagonal of BD, or x, is basically equal to 122.7. 122.7 meters. And then we could use it to calculate the missing angle. So let's do that. So now we have, let's just say x squared is equal to, let's look at the triangle. We have 135 and 60. 122.7 all squared is equal to 135 squared plus 60 squared minus 2, 135 times 60 cosine, and let's just name the missing angle as theta. So, and now let's get cosine theta to be the subject of this equation that we have here. So cosine theta, or let's just say theta, will be equal to the inverse cosine inverse and let's just send everything to the other side. So we'll have 122.7 all squared minus 135 squared minus 60 squared is all over negative 2 times this. And yeah, there we go. This is what theta will equate to. And let's just input this in the calculator. Theta here will actually equal to 65.3. Yeah, and this is how you use the cosine rule. Okay, let's analyze this triangle and see what we're dealing with. We have two missing stuff, an angle and a side, angle x and side y. And angle x is very easy to calculate, since we know that all the angles in a triangle will add up to 180. So we can just say that as x is equal to 180 minus, and then let's just add up the angles we have. 57 plus 39 plus 39, and this will equal to 180 minus x is equal to 84 degrees. All right. And now that we have three angles, we could basically use any rule, by the way. We could either use sine or cosine to calculate for y, but I'm assuming that the sine rule will be easier to use. Let's just write 84 degrees here. So I could just say, since we're calculating for a missing side, so we're going to use the sine rule, but for the missing side. So we'll have y over sine, and what's opposite to it? 57 is equal to 7.5 over sine 84. Okay, I just wanted to rewrite it properly. So yeah, we only have one missing variable. We could just multiply both sides by sine 57. So y is equal to 7.5 times sine 57 over sine 84. Let's just put that in the calculator. So that will approximate to 6.32. 6.32 meters. Please let's not forget the units. And lastly, let's just solve a question on the formula of the area. So we're given this triangle with sides that are given as x and x plus 2 meters. I'll just write the meters here. And the angle between them is 150. And we're asked to find x, obviously. So if we just easily, we know that area, which is equal to 5, so we could just say 5 is equal to 1 over 2 times x plus 2 sine 150. So if I just multiply both sides by 2, I'll be left with 10 is equal to x squared plus 2x sine 150. If I divide both sides by sine 150, then I'll be left with 10 over sine 150, which is basically equal to 20. So 20 equals x squared plus 2x, and obviously x squared plus 2x minus 20 is equal to 0. So I'll have solutions of x. Just easily put this in a calculator. Sorry, I had to get a different calculator because mine doesn't show it as thirds. It just gives it as like this, like as an actual value. So it'll be left with -1 plus minus root 21. So obviously there's could only be one solution. So we'll take -1 plus root 21 as our solution. So that's what x equals to. Okay, lastly, we're going to solve this question and then move on to the next topic, which is graphs of sine, cosine, and tan. So we're given this, and we have three variables that we're supposed to calculate. We have two angles of x and z and a length of y. So what I could see is that there is no way I could easily, like, instantly calculate any of them. So what I'll have to do is just do some calculations on the top of my head. And I only have three formulas. Remember, I have the sine rule, I have the cosine rule, and I have the area rule. Area is out of the equation because I do not know what the total area is, and I have three variables, so that's out. The sine rule, I cannot use it because I'm dealing with two missing angles, or three if you want to count this. So the only thing I'm left with is the cosine rule. And I have three sides, so I can indeed use the cosine rule. So let's calculate this angle. You could either ways calculate any angle, but just for preference, I want to calculate this. So we have 20.4 squared is equal to both sides squared, 12.3 squared, 3 squared, plus 15.6 all squared, minus 2, both sides calculated, multiplied I mean, and then cosine, and let's just name it theta. So I know cosine theta, or I could just say theta will equal to cosine inverse of 20.4 squared minus 12.3 squared minus 15.6 all squared all over -2 multiplied 15.6, right? Yeah, times 12.3. So if I were to calculate this to get theta, give me a minute, I'll have theta equaling to 93.2 degrees. 93.2 degrees. And let me just go here and name this theta. So I can now use the sine rule to calculate both x and z. So let's calculate both. So we have, let me just, so we have 20.4. Oh no, we're calculating for angles. So we're going to use sine 20.4. No, the one I just calculated, 93.2 over 20.4 is equal to 15 sine x over 15.6 is equal to sine z 12.3. So now I have x, what's happened? X equal to sine inverse 15.6 sine 93.2 over 20.4. Is that correct? Let me make sure. Since we're calculating missing angles, so sine has to be on top. Yes, it seems to be correct. So now let me just put all this in calculator. So x is equal to 49.8. Let's just say to be 50 degrees. We have x equal 50 degrees. And since we have now two angles in the triangle we have, we can now just find z such that they all add up to 180. So we have 180 minus 50 minus, we said 93.2. Let's just assume it to be 93, just for simple sake. So we have z will round up to 37 degrees. Okay, so we found x and z. Now let's find y. Y is just basically this. So what we could do is that, let's see. Okay, I had to pause just to make sure that what I was solving was right. Let me redraw the triangle in just a very short form. Or let me only draw one side of it. Let me just change the color. Don't we have this triangle? Let me draw it to be a bit bigger. So we could assume this to be y. This will be x. This is a right angled triangle. We don't need to find this. This is easy. And we have this to be 12.3. So what I could do is that I could calculate sine x, which either is equal to y over 12.3. So I have y is equal to 12.3 sine x. And we already have the value of x, so let's just calculate this in the end. And let me just say that x is equal to 50 approximately. So once you put this to the calculator, 12.3 times sine 50, you're going to get 9.4. So y is nearly 9.4 meters. So there you go. This is all you need to know about sine, cosine, and the area rules. The graphs of sine, cosine, and tangent, and there's really not much in them because either ways, most of the questions in the textbook are just going to be transformations of these graphs, and we already talked about transformations. So this is a graph of sine. If we're going to start from the domain of 0 until like infinity, so we're going to see that at 0 and 0 origin, it's going to be at 0. And then once you hit 90 degrees, it will be 1. And then once you reach 180 degrees, it will be 0, 270, negative 1. And this loop will start to repeat itself. If we were to continue, it will go like this. Like this, like this, like this. And each significant point, you just add 90 degrees to it. So you see at 1, it's 90. And another significant point, like when it reaches 0, and on the x-axis, sorry, on the y-axis, it's 180. And then when it hits negative 1, it's 270. When it hits 0, it's 360. So each significant point, as when you continue this loop, you just add 90 degrees, and that's what you'll get. For cosine, it's actually a reflection, or you could say cosine is actually the derivative of sine. So it's going to look really similar. So at x equals 0, y equals 1. And it's going to repeat itself like this. So this is how cosine looks like. It looks different because either way, tan represented is basically the ratio of sine to cosine. So you'll realize if you look at the origin and you add either 90 or subtract 90, you're going to hit an asymptote where basically the actual function itself, if you were to plot out the points, they will never touch these lines. I know here it touches, but like here it won't touch. Here it won't touch. And if you add 90 to 270, it won't touch. And if you subtract 90 from the origin, or x equals 0, it won't touch. At 270, it won't touch. So these are the asymptotes in which the points of the function actually won't touch these. Won't touch x equals 90. It's basically unknown. There's no value to that. And either way, the questions in the textbook, as I mentioned earlier, it's going to just be manipulations or transformations or translations of these graphs, and they're pretty easy. There's nothing to know about it. So yeah, and that's chapter 6 for you.